Hello and welcome to 10-Minute Physics. I am the physics exam guru. Today in 10 minutes or less I would like to look at some exam tips. Part 1 is going to be us looking at reading the question and interpreting the question correctly so that you are writing an answer that they are looking for and not talking about irrelevant kind of side-related issues. In Part 2 we will look at making the jump from a GCSE, IGCSE level explanation to an A-level or IB explanation. We'll also take a look at using your formula to help guide your written answers, using the equations that you should know, using the logic of them to help you figure out what you need to write. All right, without further ado, let's go on and look at this question here, number 1, okay? So there's a setup here. This is a demo I had done in my class. We had talked about, and I'd done like an online demonstration. ophysics.com has a really good electromagnetic induction simulation, I guess, if you will. It's interactive. And yeah, you drop the magnet through, and we know that we should have some field lines coming out. Coil will cut the field lines, however you want to word that. And you get this EMF induced. And you can talk about why this happens, and you can talk about Lenz's law and Faraday's law and that kind of thing. But if you take a look at the question, explain the shape of the graph and the relative values on both axes. You'll notice that, as I've said to my class now, this is not technically a physics question. It's more of a mathematical interpretation question. And as you should always be in trying to improve your written answers, you can get better at explaining, and some of my students did fairly well explaining, the Lenz's law aspect and the electromagnetic induction, but they just want to know about the shape of the graph. Okay, so you will have covered this in class. You should know a few things. So you should notice that the time here is a little shorter for the second dip. Now, you know that these areas should be the same. These areas represent something. Okay, induced EMF. Let's just see. If I go back to my note 3. You know that your EMF is equal to the rate of change of flux. Okay? So this is dependent on time. And so if EMF is rate of change of flux and you are multiplying by time, the area under the curve here is the flux. And the flux should be the same all throughout. Okay, why should the flux be the same all throughout? Well, your flux is equal to NBA. The number of turns in the coil is not changing, right? The flux density, the magnetic flux density of the magnet that you are dropping through the coil, that's not changing. And the surface area of the whole coil is not changing. So nothing is changing there. The only reason that the EMF is induced because of this rate of change of flux is because when the magnet is away from the entrance to the coil, you don't have as many field lines going through in the coil. As it gets closer, you'll have more field lines within that coil. Okay? So technically, this is the reason why the area of the graph needs to be the same, because the total flux over that time, the total change in flux over that time will be the same, right? Your area here, right? The area under the curve is the rate of change of flux times a small incremental change in time. So that cancels out, and you have the area under the curve should be flux. So that should be constant. And that's what you center your answer around, okay? In the interest of time, I'll just go to the mark scheme. Look at what you talk about. We know that these areas should be the same. Now I'm going to work backwards here. Why should they be the same? Well, we know that the time for the second pulse is shorter. Why is the time for the second pulse shorter? Well, the magnet's dropping through the coil, and because it's dropping through, we know the speed increases as it falls. And if it's going to go through the latter half of the coil quicker because it's going faster, then the time pulse will be shorter. We know that, okay? Why is it going to be negative? Well, because it's leaving, it's going, okay? But also negative on the way out is going to be larger, yeah? As you see, yeah? This peak here is greater negatively than it was here positively. Remember that this is rate of change of flux. Your other equation for your EMF is BLV, Okay, the B is not changing. The L is not changing. It's the velocity of that magnet as it moves through, which is changing. So you should see a greater peak here. Yes, it's negative because it's leaving, but it's greater than the positive peak when you first have the magnet enter. And so that's that point there. Okay, we've practically got the marks that we need. So what else could we have said? Well, you could have identified the negative gradient as it's going through the coil. You know that it's going to change, but at some point, if I draw my magnet here, once all the field lines are actually, within the coil, there is no change in flux. I would say yes, it will be zero when it's exactly in the middle for that split second symmetrical in the coil, but they're not asking for the physics of it. They're not asking why the graph is shaped, why the graph is produced. They want you to explain the shape and the relative values on both axes. And so that's what we've done here. That's what we've done here, talking about the areas, talking about the time, talking about the negative EMF being greater than the positive EMF. Okay? Talking about why that happens, because the speed is increasing. Okay? That's the only real physics part.
Oh, and speaking of gradient, if you've got the gradient of this graph, it's the rate of change of EMF. And your EMF is equal to that BLV. B and L are constant, but the rate of change of V is acceleration. That means the gradient of that slope there is probably equal to G, because that's the acceleration due to gravity.
You can go back up. You can say, hey, we got a changing flux. Okay, the cutting of the field, the flux is changing. The induced EMF is proportional to the rate of change of flux. Yeah, that's what I had said here. In that you know this from your formula. So again, I want you to read the question to make sure you're not explaining Faraday's and Lenz's law. You're explaining the shape of the graph. You can use the formulas to do it. Yeah. And what else? What else do you got here? The initial increase as it gets closer to the coil. As it gets closer to the coil, you'll have it's because it's proportional to the rate of change of flux. So you can, say a sentence there, 1 mark, talk about the time, talk about the area, talk about how the negative max here is greater than the positive max. And I think you add up a bunch of those and you'll get your 6 marks. But you got to read the question. Students will see a question like this and think they need to explain Lenz's law and that kind of thing. Okay, now, that's probably because there's a question that exists out there where you do have to explain this graph in terms of Faraday's and Lenz's law. Okay, but read the question.
So that's going to end part 1. I'd like to see you in the other video where we'll continue to talk about how to upgrade your answer from a GCSE level to an A-level understanding, and we'll continue to look at how we use the equations to answer written work. A lot of students tend to think that it's either a written answer or a mathematical answer, but you can actually use the mathematical equations to help guide what you would write. We'll see that in part 2. Hope to see you there. Until then, I've been the Physics Exam Guru. Thanks for watching, and we'll see you in the next video.